this episode, we will focus on how simulation techniques can be used in the field of reliability, availability, maintainability, and safety, or commonly known as RAMs. So in particular, we're going to focus on how engineering companies can move to model-based workflows for RAMs and how that can help with the modern-day challenges of engineering complex systems. So with me today, all the way from Melbourne, Australia, is Chris Stecki, CEO of PHM Technologies. Welcome, Chris.
Thanks, Finan. Thanks for the opportunity.
No problem. So I guess let's get straight to it. So, firstly, can you help explain some of the challenges that companies face, particularly within, say, the aerospace and defense sector, with regards to certification and assessing the safety and reliability of their platforms?
Yeah, right. So I think the key thing is to understand that the primary goal of RAMs, as you described before, is really to identify, analyze, and mitigate technical risk that exists within a particular design configuration. So I think the most important thing that has impacted on the RAMs domain has been the increasing complexity of systems. So the more complex the system, the more potential failure modes exist within that system, the more ways things that can potentially not meet their intended function. And if you don't identify a risk, what that leads to is, downstream impacts of having to mitigate that risk once you're in operations. And that's obviously a lot more expensive. So what's really important, and we've seen, some recent well-publicized, events in the news about what happens with, getting things wrong in the aerospace domain, and how that relates to certification. So there's actually more of an emphasis at the moment on being able to identify that risk early enough in the design process that you have an opportunity to design it out, and then being able to consistently and accurately describe the risk and the mitigations that have been taken in relation to that risk in order to support that certification piece. So, the most important thing, I think that the biggest trend has been around this increasing complexity, and also the fact that typically now organizations don't do the complete, they're not owning the complete design. They've got a supply chain that's providing subsystems or components and so on. Being able to understand and, assess the potential impacts of the failures that might occur within these different subsystems and so on, leads you then to having that increasing complexity. And again, that's the biggest thing. If you don't identify the risk, you can't mitigate it. So that's what's the most important aspect of things.
Okay, yeah, makes sense. And engineering teams at these companies are tasked with producing numerous reports and artifacts, some that are required for certification, for example, and for building condition-based and reliability-centered maintenance strategies. So what are some of the issues that these companies and these teams are facing, using conventional approaches?
Well, I mean, the first thing to say is that, the domain is fairly well understood by those mature companies. And I guess it's that level of maturity that's the key determinant. But if you're really looking at being able to identify all of that risk, it comes down to a trade-off that you have to make in relation to the accuracy, the granularity of these RAMs analyses, and what impact that has on your design or certification schedule. I mean, there are some statistics that indicate in the aerospace domain that, it's the same amount of schedule and cost to actually develop the design as it is to certify it. So obviously, if you can reduce the analyses and the schedule that are required to conduct that RAMs analysis and to be able to record that in a way that's going to be suitable for the regulators, that's the most important thing, because then you have the ability to understand the impact of your RAMs studies on that design process, on the design life cycle, if you will. I think the other thing that's really important is the consistency of the way in which these analyses are being performed. So when you are looking at a manual approach, which is predominantly what people are using now, First of all, they're leveraging essentially biological domain knowledge. It's the knowledge that's captured in the minds of the teams that are working on these projects. But it's really important, I think, that we need to transition to a more objective, repeatable, traceable mechanism for identifying that risk. And there are also downstream impacts in relation to who actually owns that risk. So if you have a supply chain where your trade partner, your design partners are providing you with subsystems and so on, you want to make sure that they've exercised the same amount of diligence in performing their RAMs processes, their analyses, as you do, because if you're the prime system integrator or the OEM, you're the one that takes responsibility for that in the eyes of the regulator, and obviously in relation to the customer and the industry. So, I think it's really important that people understand that yes, these techniques have been used for many years, but feeding back into that complexity issue, it's becoming almost impossible to go through that process with the range of potential failures that need to be understood, documented, analysed, mitigated. That scope of work is becoming unmanageable for some of these more complex systems, particularly in aerospace and defence. And a prime example there would be the eVTOL or the UAM market. At the moment, we think the industry is spending a lot of time on developing the actual design and testing the designs and so on, but they're not paying sufficient notice really to the certification piece, which is potentially as big or in some cases larger than the actual design process. So yeah, I guess the key thing that we see is this productivity, so that you can actually perform these RAMs analyses at the point where you have the ability to influence the design itself, rather than simply document the flaws essentially that you've left there because you haven't been able to complete the RAMs appropriately.
Right. Yeah. So I guess my next question is, and you've kind of explained there how these kind of manual based processes are not able to deal with the rising complexity in these systems, as you explained. So I guess the question is, what could we do differently? And my question is, how can we use a model-based approach? And what would be the benefits there, and how would they help these challenges?
I think the first point I'd make there, Vinan, is that across the engineering domain, digitalization or digitization is prevalent. So most tools have already been digitized, and I guess it's ironic in a way that RAMs, which it's pretty important. It's a pretty important function. I mean, its safety and reliability are rather important, we tend to think, particularly for mission and safety critical industries, commercial aerospace, defense, oil and gas, transport, mining, all of these things where there's potential loss of life or significant loss of productivity, economic impact. It's really important that we find ways to effectively offset that risk. And if you bring RAMs back to its core function, it is to identify and mitigate that risk. So, for all the reasons that we've had digitalization across the industry, I mean, the reason we've gone from using Draftsman with paper and pen into 2D CAD, then 3D and so on, that transition hasn't yet occurred in the RAMs domain. And, one of the inhibitors has been that there haven't been these types of tools. There hasn't been a variety of model-based solutions that allow you to perform this. And I think that's the interesting piece now, is that there is now work being done to identify how models can be used to support and augment that RAMs process. Really important to note there, models aren't going to replace engineers. What they are is an efficiency. They're a productivity tool, essentially. And what we want to do is we see that using a model-based approach to RAMs will effectively transition the role of the RAMs engineer away from transcribing documents and into Excel spreadsheets or similar, and instead being able to leverage the outputs of these model-based tools that are conducting these analyses, effectively autonomously almost. But they're auto-generating these analyses. And what we want the engineers to do is to actually leverage their experience and their training and their knowledge to interpret the results of those analyses and inform those design decisions going forward. So, really what we do, we see that the key benefit of digitalizing or using a model-based tool for RAMs will be to enable the engineers that you have, the function, the expertise that you have within your team to be applied to analyzing and making better decisions around how that design configuration needs to be modified, perhaps, right, to achieve those safety and reliability goals, rather than spending the majority of their time simply documenting, what potential failure modes or flaws or that they believe might exist. So I guess the two things that we would see is that the primary benefits of a model-based would be, one is to have that consistency and accuracy of the analyses that are being performed. The second would be that it frees up the existing engineering function that you have to be able to apply their knowledge. So you get a value add from the engineering rather than, as I say, data entry, data management, which we think is, typically not why the engineers go to school for all those years.
For sure. So that kind of takes me to MAID, and I guess, could you explain how MAID can help with what you just described, with moving towards this kind of model-based world? Yeah,
thanks. So essentially what we've been able to do is to create a digital risk twin. Now, everybody talks about digital twins, and every digital twin's should have a purpose. The risk twin, the digital risk twin that we're able to provide for a system allows the engineer to essentially create a model that shows the functions and the interdependence of those functions within the system configuration, within the design. Once you've created the model, there's an analysis platform that that MAID provides to be able to interrogate that model to achieve a variety of different analyses. So a lot of these are interdependent. For an FMEA, for example, we need to know how the item's intended to function, what's going to happen if it fails, why it fails, and what's going to happen to the rest of the system in terms of how is that going to impact the behavior or the functional capability of the system if we lose one particular component. And so the key thing that MAID does with this digital risk twin is it automates the process for identifying how those failures can occur and what those up and downstream impacts of that failure will be. And essentially what that does is gives us a signature, a unique signature for all of those disparate and discrete technical risks, from the cause to the mechanism to the fault to how that leads to a loss of function, how that loss of function translates across the system. And that piece of information allows us to then automate the generation of FMEAs, fault trees, reliability block diagrams, and so on. And it feeds into a number of workflows. So, I guess the two key aspects are that the model allows you to create a digital risk twin that you can mature along the design cycle. So you can start with a conceptual model. As you progress your design, you can add more granularity to that model. And what that means is you're now starting to do your RAMs concurrently, which actually means that you've got an ability to influence the design. If you understand what the risks are and where there's a potential impact on the through life, the requirements you're going to have to maintain this system based on what you can see as a reliability or a safety issue, it's a heck of a lot cheaper to be able to modify that during the early design rather than waiting till it gets out into service and then having to go back and update that design and then recertify and so on. So I guess automating the analysis is really important. Being able to provide that analysis capability concurrently through the design is really important. It also has a sort of an interesting effect by capturing essentially the understanding of the system of your engineering team, and to put that into the model. Effectively, what it does is digitize the domain knowledge that you have, both internally and with the supply chain. So, if we talk about aerospace and defense, a lot of these platforms are, in service for 10, 20, up to 30 years. It's fair to expect that the senior engineers that were there in the early stages aren't going to be there to answer questions later on. If you can capture the narratives, the assumptions, the comments, and associate that with the model, so that when analyses are generated, we can say, well, why did they do that? And we have that information associated. It means that you can leverage that digital domain knowledge across the life of the platform. And we think that's really important, particularly for these long life platforms. So
right. Yeah, and MAID is a fascinating tool, and you talked there about integrating analyses, capturing knowledge, and working with design. And we, at Siemens, we talk a lot about the digital thread, and connecting all these pieces together. Can MAID fit within that kind of broader digital thread that Siemens provides?
Absolutely, that's one of the reasons that we're very, very happy to work with Siemens, because we see this. Obviously, RAMS is not a function that works in isolation. It's one of the components that goes into an effective design process. And obviously, while we think RAMS is the most important because that's the domain that we're in, we recognize that there are many other important functions. And so a lot of the information that RAMS generates is actually used in other areas. So, for example, understanding what the risks are, understanding when they're likely to potentially manifest, and therefore understanding what maintenance you'll have to put in place, what the regime of maintenance will be, whether it should be condition-based or whether it should be scheduled or wait for it to break and then fix it. All of these outputs, if you will, from the RAMS process feed into other downstream analyses that are performed within that broader PLM environment. So if you look at that digital thread, we see that the digital risk twin is one of the twins that are associated to the fabric of that thread. And it's really important for us, for example, that MAID is able to interface with systems engineering functions or service lifecycle management functions. And being able to fit into that broader digital thread means that you've got the interoperability to be able to do that. And that's really important. And I think that, as a function, RAMS has historically, because of the tools, because it's manual, because of the time it takes to do it, it has often been done later in the program where it's actually too late. By bringing it into the digital thread and by making it part of that whole digital journey, it means that you've got the ability to perform that RAMS function early, and you therefore get much better impact, much better outcomes from applying the RAMS process to your design process, both for the original design optimization and certification process, but also because the RAMS data, the RAMS knowledge is an effective, it's an input into a lot of the AI that people are trying to develop for, Industry 4.0, looking at predictive maintenance and so on. So the RAMS model is a really important contextual understanding or representation of the system that will enable people that are looking to apply AI, for example, in operations, to have that engineering context around those AI techniques. And we see that's really important. So, I've tried to hit there a couple of the key areas where we think we tie into the digital thread, but I think that the most important thing is that there is interdependence and interoperability between a lot of these different functions: systems engineering, RAMS, design, service, maintenance, diagnostics. They all have some degree of interdependence, and that's why it's important to have that digital thread. You want to be able to make sure that all of the data is available. You've got, you know, effectively a single source of truth. Everybody's working off the right data at the right time, and you can configuration manage it, because that's the other really important piece. If you you know, if you're not doing your analysis on the latest version of the design, it's effectively wasted. So yeah, concurrency, consistency, and interoperability are you know, the most important reasons we think that, you know, any RAMS function should be incorporated into that broader digital thread, that PLM stream.
Great.
And that feeds into, you know, our goal. We want to be the industry standard for model-based RAMs. So, but we're always interested to talk. So, you know, if you haven't spoken to us, please do.
And with that, yeah, and thank you, Chris. And it definitely is an exciting technology, and I do encourage folks listening to not hesitate to contact you know, Siemens, and we'll have our contact details provided in this video as well. So that brings us to the end of our time in this episode. So I'd just like to say thank you for your time, Chris. It was great talking to you.
Thanks again, Vinan.
Thanks a lot. Bye.